Hello, everyone. My name is Valentina Zhang, and the title of my presentation today is Individualized Facial Emotion Recognition through Dual Representation and Group Established Context. The goal of my research is to improve FER accuracy, which is critical to clinical care and many other FER application contexts that are sensitive to errors. First, let's take a quick look at some current limitations of the known FER approaches and establish our problem statement. Our research focuses on three main limiting factors in the existing approaches that are critical to FER accuracy. First, facial representation. Second, emotional state ground truth. And third, deep learning model training data. In this presentation, we will explore the alternatives on these three dimensions. In the case of facial representation, our FER system arbitrates between two facial representations, instead of relying on just a single representation. Ground truth is an extremely challenging issue in FER. The best known approaches have been relying on professional actors, although recent studies have shown that facial expressions of trained actors are quite different from the rest of us. In this research, we propose using group behavioral context to automatically derive ground truth. Lastly, we experiment with a way to establish individualized data instead of relying on universal data. Putting all three improvements together, we will show some preliminary yet promising results. But before I get into the details of my research, I think it's helpful to provide a brief introduction on the scientific foundation of FER. Emotion science traces its roots back to the times of Charles Darwin and William James. Within the Western thought, cognition or thinking and emotion have traditionally been conceived as adversaries. However, Darwin and James discovered that it is also possible to understand emotion within a cognitive framework, or to treat cognition and emotion as integrated neural networks. In the context of facial emotion recognition, Darwin established that facial expressions have robust causal relationship with emotional states. James went further and asserted that facial representation is chiefly responsible for emotional state. In other words, if you don't show an emotion, you're not feeling that emotion. A modern mind hack along this line is the trick that forcing a smile on your face will automatically cheer you up. It worked pretty well for me, so please feel free to try it as well. Now, fast forwarding to recent times, there have been three most cited research that have established the importance of facial emotion recognition. The first one is from Albert Moranbian that have shown that facial emotion plays an important role in communication. He concluded that words only represent 7% of human communication related to emotions and attitudes. All of the rest come from nonverbal sources. Tone of voice accounts for 38%, and the remaining 55% comes from facial expressions. In the second research, Paul Ekman proposed 7 universal emotions. Subsequent scientific research have classified 6 facial expressions, which correspond to distinct universal emotions: disgust, sadness, happiness, fear, anger, and surprise. In the third groundbreaking research, Solovey and Mayer conceptualized emotional intelligence and its significance. From a scientific standpoint, the research claims that emotional intelligence is the ability to accurately perceive your own and others' emotions, to understand the signals that emotions send about relationships, and to manage your own and others' emotions. Today, FER is being put to work in many useful application contexts. Take human-computer interaction, for example. FER has been shown to hold undeniable benefits in certain situations, such as driving. Human factors like distracted driving, which ranks among the top contributors of road fatalities, could be all but eliminated following an adequate introduction of FER-based systems. In fact, proposals to mandate the use of such devices are being introduced worldwide. Now let's take human-human interaction for another example. Our FER technology has reached a point where it can monitor or even manipulate mental states as a means of cognitive enhancement for professionals like physicians or pilots, and many others, which can lead to effective learning and communication. FER applications also exist in a non-interaction context. Let's take self-care, for example. There's been a recent report that showed that a clinically proven AI-powered mental health chatbot called Tess had over 29 million people with paid access. It turns out that when it comes to mental health, people prefer confiding with robots than humans. And finally, FER is being considered by some as a gateway towards truly intelligent machines. Some research have even proposed that emotion may be the last piece of the puzzle for creating natural intelligence and conscious being. Now, here's a roadmap for a typical FER system implementation. It starts off with face recognition. Our research uses a standard algorithm from the OpenCV library for this step. So this presentation will not discuss more on that, other than just to point out that we rely on OpenCV to recognize that the pictures on the right do not have faces in them. We humans see faces in everyday objects. This phenomenon is called pareidolia and involves a particular part of the human brain called the fusiform face area. We'll see more on that later. The second step of FER is facial emotion detection. And here we make the decisions on how to capture facial expressions and how to label the data. And the last step is where we select the system architecture and the specific AI techniques for FER. Now, as shown on the previous slide, there are two dominant families of facial representation: pixel-based and semantics-based. Let's take a closer look at the two. The success of deep learning in image processing tasks is modeled upon biological vision and brain information processing. FER is no different. Take the pixel-based FER system, for example. It closely resembles how the fusiform face area in our brain processes facial expressions. The whole face is processed holistically, and no specific features are extracted or analyzed. The model we use in our system is shown on the right. It's a fully convolutional neural network composed of 60 convolutional and separable convolutional layers and has a 60% training accuracy. And now, before I introduce our landmark-based model, let me talk a little bit about facial landmarks. These 68 points on a face anatomically define face action units, or AU, which can be mapped directly to the 6 universal emotions. Such a suitable representation of data significantly increases the accuracy of a model. In humans' face recognition system, the occipital face area in the brain recognizes the eyes, nose, and mouth as individual pieces, which is quite similar to a model trained on facial landmarks. The occipital face area, or the OFA, recognizes the facial structure and outlines of shapes, which resembles how landmark-based FER processes facial expressions. The landmark-based FER model we use is a fully connected ANN with 2 hidden layers of 128 neurons using the rectified linear unit activation function and Animax optimizer. The model training accuracy achieved is 56%. Now let me talk a little bit more about some of the neuroscience inspiration for our research. In the human brain, a region called the fusiform face area encodes face identity information holistically. This resembles how a model trained on full images would function. On the other hand, another region of the brain, called occipital face area, is more sensitive to extracted facial features, such as eyes, nose, mouth, which resembles a model trained on facial landmarks. Our hypothesis is that a model trained on full images and a model trained on facial landmarks can offer complementing views of emotions. So we did a comparative study to analyze if indeed the pixel-based model and landmark-based model provide complementing views of emotions. The results are very interesting. Here's one example based on a very popular deepfake video on YouTube. The one on the left is Elon Musk's original video, and the one on the right is Robert D's fake. From the correlation heat map on the right, we can see that the landmark-based model picked up a strong emotion correlation between the two because the deepfake uses a landmark-based technology. In comparison, the pixel-based model did not find nearly as strong a correlation. Deepfakes do not take emotion into consideration because translating a perceived emotion from one face to another is quite difficult. So, at a pixel level, there are many differences in emotions between these two videos due to the loss in translation. Now, taking a closer look, here's a quantitative analysis of the same example. We manually analyze the complementary metrics for both models. Since the overlap in true positives, which is 33% and 25%, is less than 51%, we conclude that the models provide complementing views in FER. The lower figure displays the emotions that the pixel-based model picked up in the two videos. We can see that at some times, the deepfake seems to be angry as opposed to sad. Based on the metrics, we hypothesize that the two models could be orchestrated to deliver better FER performance. Before I move into the group emotion synthesis and modeling, let me explain a few important concepts that our research references. These concepts characterize three group engagement levels. An engaged group could reveal information about the interactions between individuals. However, many group-wide events are still pretty unpredictable. A synchronous group shares the same emotion change cadence. Labeling could benefit from knowledge of group-wide events. A homogeneous group shares the same emotion. Labeling can directly benefit from group emotions. Now here's an overview of our FER system architecture. From the left are the two FER models already discussed. The recognized emotions are fed into the FER Noise Reduction component to eliminate transient interference. After that, we synthesize the group emotion, which is used for two purposes. One is to use its change cadence to adaptively orchestrate the two FER models in the adaptive FER inference component. And the other is to use its emotion value as the ground truth label for training data generation. Notice that there is a feedback loop at the bottom of the diagram where we maintain the group emotion state. Although this research is only interested in simply using the group emotion as the ground truth label, the group emotion state could also be used for modeling and prediction as well. Now let's dive in and look at each component with more detail. In the FER noise reduction stage, we target transient interference in facial expression, such as speaker's mouth movement or video jitters. We use DFT to remove low energy frequencies so that the later components could work with more stable data. In the DFT formula to the right, the lowercase x are thought of as the values of a signal at equally spaced times t equal to 0, t equals 1, all the way to t is equal to n minus 1. The output uppercase kx is a complex number, which encodes the amplitude and phase of a sinusoidal wave with frequency cycles per time unit. In group emotion synthesis and cadence detection, we first synthesize the group emotion by summing up the probabilities of each emotion type from all group members. To account for polarizing group sentiment, we use the Euclidean distance to check for deviation above the threshold. Group emotion may also be noisy, so we use DFT again to eliminate noise. The goal of this component is to create the reference emotion change rate for adaptive FER inference. And now in the adaptive FER inference, we use the group emotion change cadence as a reference to adaptively adjust the weight function. When the individual change rate is higher than the group, the weight for the landmark-based model increases. When the individual rate is lower than the group, the weight for the pixel-based model is increased. When comparing the change rates, we compute the correlation so that the delta reflects the incorrect emotion readings. The details of the algorithm is to the right. Now here's an analysis of our adaptive FER against the non-adaptive, where pixel-based and landmark-based models carry constant equal weight. In the first test, the adaptive model took 20 seconds to adjust and show some differences, but afterwards detected false positives of SAD from the traditional model. In the second test, the adaptive model detected false positives of fear as well as angry emotion. Manual analysis did in fact confirm these findings. Using the group emotion as ground truth label, we retrained the DL models with individual data. As an example, the orange line from the retrained model is able to identify the inherent SAD component in this particular group member's facial expression. Additionally, the false readings of fear and angry due to unrelated facial changes were also detected and compensated for. The group must exercise the full range of emotions for such retraining to be effective. And now here is a summary of the threats to the validity of our research and what we have done to mitigate them. First, construct validity and complementary metrics of the image versus landmark based model. We support this claim through two analyses. One, complementary metrics, and two, correlation test. Internal validity, which could consist of possible subjectiveness when manually evaluating the group emotion. To mitigate such a threat, we used two-judge agreement and qualitatively discussed false positives and borderline examples. And lastly, external validity. We studied a small number of pre-recorded videos that may not generalize to larger or other group contexts. Now, in conclusion, our experiment found that the pixel-based and landmark-based facial representation models can provide complementing views of emotions. We have constructed an adaptive group emotion recognition system, learning from both models for better FER accuracy in didactic or small interacting group contexts. And we propose a method to use group emotion as the ground truth labels for FER personalization. And lastly, we demonstrated FER accuracy and personalization, which are highly desirable in autism care and other contexts, applications sensitive to errors, which can benefit from our approach. And now, as for the next steps, we would like to validate our approach with more real world data and group contexts. We also want to enhance the fidelity of our facial representations and the sophistication of our adaptive algorithm. In terms of training data, we want to experiment with finer grained emotion models. And lastly, the biggest challenge in FER is the ground truth. To that end, we are experimenting with more multimodal data involving vocal, physiological, neurosignatures, and contextual information. Additionally, as this research showed, emotional ground truth could also be established through a behavior or social context. Like the most studied facial emotion of Mona Lisa, the truth could be hidden in unexpected places or in plain sight. Finally, my heartfelt appreciation goes to Dr. Neha Keshav and Dr. Ned Sahin at Brain Power LLC, Ms. Morgan Henry at Meta Facebook, and MIT Beaverworks Summer Institute. Thank you all sincerely for making this research possible and making me a believer in human emotions. Now at this point, I'm ready for some questions. To those of you who can see a human face in my question mark, the fusiform and occipital face areas of your brain just got activated again.